Hey everyone, in this video we're going to be talking about how to perform a momentum balance when developing our process models. In a previous video, which I will link in the description below, we talked about the general balance equation when developing process models. Before we begin, I just want to reiterate the process for developing ODEs from mass, energy, and momentum equations, as it is very important. First, you should draw a diagram or some visual version of your system. Then we need to identify a region of interest. This can also be known as your control volume. Then you perform the appropriate balances, check your ODEs to make sure that they make physical sense, and then lastly, you check to see if your ODE is consistent and has 0 degrees of freedom, which means that it can actually be solved. Just keep this list in mind as we work through the rest of this video, and if you have any problems of your own to solve, consider writing this list down so that you don't rush ahead and forget any important steps. So, finally, let's get right into the problem. Let's create a simple problem in which the only quantity that we are interested in is the momentum, more specifically the fluid velocity leaving a small outlet. So let's say that we have this tank here, and to increase the outlet velocity of our tank, we have a small outlet that is driven by the weight of the fluid in our tank. We can also assume that this system is isothermal, which means that it is at a constant temperature. So, to begin any balance problem, we need to identify our area of interest. That is the area or region we should observe a potential change in accumulation of our fundamental quantity of, so momentum for us. Well, for us, it makes sense to observe the pipe outlet as this is our region of interest for the momentum balance. And to note that this is our control volume, also known as our volume of interest. So, now that we know where we are going to be observing for changes in our system, let's write our general balance equation that we talked about in a previous video. Now, remember that this equation is for all 3 fundamental quantities and is incredibly important. So, the first thing we do is eliminate any of our terms in our general balance equation that we do not need. We know that we want to solve for the velocity change out of the pipe as a function of time. Therefore, we need an accumulation term, as we know that the velocity is going to change with time. We are also going to have hydrostatic force forcing the fluid through the pipe, therefore we have a generation term. We also have friction within our pipe, which consumes some velocity, if you will. Therefore, we do not have a proper inlet and outlet, and we can simply cross these out. Well, the accumulation is just going to be the rate of momentum change over the time change, right? Well, momentum is simply the mass times the velocity. Therefore, we have the velocity times the density times the volume, which is just the area of the pipe times the length of the pipe. This is going to equal the generation term, which is the hydrostatic force, and then minus the consumption force, which is the friction force within the pipe. For the hydrostatic force, we have the density of the fluid times gravity times the area of the tank times the height of the fluid in the tank. This all works out to the units of newtons, which is expected as this is the same units that are in our accumulation term. Then, lastly, we have our frictional forces, which can be written as a frictional coefficient K times the length of the pipe times the velocity squared. We can now remove the constants from our accumulation term. The constants that can be removed are the density, the area of the pipe, and the length of the pipe. When dividing by these constants, we are left with the following ordinary differential equation. One thing I do want to mention here is that in our friction force, we have a velocity squared term, which means that this ODE is nonlinear. And remember what we learned about Laplace transforms in the past. We cannot take the Laplace transform of a nonlinear ODE. So we will need to use some other method that is outside the scope of this video, and we will talk about this more on how to resolve these types of problems in the future. Just for now, know that you cannot take the Laplace transform of a nonlinear ODE. Alright, so now we are ready to make sure that this simple model actually makes sense. Here we select all potential constants and variables and hold them constant while altering only one value and seeing if the expected behavior is returned to us. Well, as you can see here, we have 8 independent terms. So let's just test a couple. If we increase the length of our pipe, then our velocity will decrease, which makes sense. If we do the opposite, it makes our pipe shorter, and there is less friction, and therefore the rate of velocity decrease is less, which also makes sense. If we increase the height of our liquid in our tank, then we have more hydrostatic force forcing the fluid through our pipe, and therefore the velocity will be faster, which makes sense. And again, if we decided to decrease this value, then there would be less hydrostatic force and therefore less velocity, which also makes sense. I recommend that you take a minute here and change a variable or two while holding all else constant to ensure that this ODE makes sense to you as well. Now, we need to check if our ODE is consistent and we have enough equations to ensure that we can actually solve this problem. Alright, so let's write all of our independent equations here at the top. So, we have all 8 of our independent terms here. Use this top region as a checklist to ensure that all of your independent variables are properly accounted for. So, let's add the rest of our variables to their respective categories, and as you can see here, our number of unknowns is equal to the number of independent equations, which is what we want and expected. Therefore, this ODE is consistent, which makes physical sense, and it can now be solved. In the future, we're going to deal with systems that have multiple fundamental changing properties, like a system that is filling with 2 streams of water at changing temperatures, and then we need to solve for both mass and energy. Or we have the same system, but we need to account for the momentum at the outlet as well. In this case, we have 3 equations to solve for. Do not get overwhelmed by this, as there is a lot to learn, and it can certainly be confusing at first. Just take your time and rewatch this, the energy balance, or the mass balance videos as much as you need to make sure that it makes sense to you. Thank you for checking out this video, and I hope it helped your general understanding of how we solve a basic process model using the momentum balance. If you enjoyed, please like, subscribe, and consider checking out our Patreon page to support the channel. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.